Okay.
So it just started, I think.
Yep. I think it looks good. All right. Hi, guys. I'm Bryce Sandlin from the University of Waterloo, and this talk is on lazy search trees. And this is joint work with Sebastian Wild, who you guys know. And yeah, as mentioned, this was just published and actually presented a couple days ago in FOCS for FOCS 2020. All right, so what was the problem description? So as mentioned, the rough idea is we're going to support the operations of a binary search tree. So pretty much any operation computable on binary search tree is something we're interested in. So I have some of them listed here. I'll just go through them briefly. So rank query, select query, membership, predecessor, successor, minimum, just find the minimum element, and maximum. Operations of inserting a key, delete with a pointer to a key, change key, and we'll have a few restrictions on this operation, but with a pointer to the element as well. Split, where we just split the data structure at a particular rank R into two data structures with ranks all less than or equal to R and ranks greater than R. And then merge, and this is binary search tree merge. So T1 has all keys less than or equal to T2. So as I've kind of already mentioned here, we are going to allow duplicate keys, but this doesn't actually make a difference really. In theory, we can make the keys unique if we want to just say add the insertion time, couple that with the key. But so we're going to call this the sorted dictionary problem, just to kind of give it a name. And this is in contrast to the standard dictionary problem, where the standard dictionary problem we're going to support membership, insert, and delete. And the big difference here that we'd like to emphasize is that the standard dictionary problem does not require that you maintain order. So we're going to look at these comparison-based data structures that do require this maintenance of order. And in particular, the dictionary problem, at least in practice, you can just solve it in constant time per operation with hashing. Okay, so what are the existing sorted dictionaries? They're pretty much all, up to this point, balanced binary search trees. So I just have a few balanced binary search trees listed here. AVL trees, red-black trees, and splay trees. And the balanced binary search trees give you log n time per operation for all of the considered operations. And just a note quick here, we're going to define this log function to be the minimum of 1 in the binary logarithm. Okay, there is something special about splay trees, however, and that is that they actually support these fine-grained access theorems. So I have a few of them listed here. I can try to go through them briefly. So static optimality, it says that instead of getting log n in general per access, we can actually get this log m over qi. And roughly this means that if I have an access sequence where, say, one element is accessed half the time, I can actually make the access to that element be constant time instead of logarithmic time. Now, there's another property that says it's called the working set property. And this says that we can access an element I in time log of ti plus 1. Ti is the number of items that have been accessed since I was last accessed. And then there's a dynamic finger property, which says I can access key I in log of the difference of the previous key accessed and the key being accessed in current iteration. This is the number of keys between I and j. So they're kind of interesting theorems that show you can get kind of beyond this log n per operation time complexity. And this has been studied quite a bit, and there's this conjecture that actually says splay trees are really as best as can be in the binary search tree framework. So specifically, it says splay trees are constant competitive with any other binary search tree on any sufficiently long access sequence. This conjecture has received quite a lot of attention. I have some of the major papers in this line of work listed here, and I'll briefly go through them. The the first one is the original splay tree paper by Sleater and Tarjan. This is where the conjecture was proposed. And then in '89, in a SciComp paper, there's this so-called Wilbur lower bounds were established. And this kind of establishes this model of computation that if you're going to have a binary search tree, you have it just formalizes you have accesses from the root, and updates are going to be the form of rotations. And just a few more here. Dynamic finger property was proved in the 2000s. The working set and dynamic finger properties have been generalized, the unified bound. There's been work on actually getting a log n competitive binary search tree. And there's also been another data structure that's received a lot of attention that's also proposed to be dynamically optimal. And it's called this so-called greedy BST here. So yeah, just the rough idea I'm trying to establish here is there's been quite a bit of work on the dynamic optimality conjecture. And yeah, this continues to see a lot of attention in the most important theoretical computer science venues. And so this is kind of the big motivation by our work. And really the idea here is, so we've done all this work considering binary search trees and how efficient can we make a binary search tree. And in some sense, this is not the right question to ask, because if you're actually consuming the data structure, we don't really care what form the data structure takes. What we care about is what operations are supported and how efficiently those operations can be supported. So in this dynamic optimality literature, we have this like access time, which is just the time to go from root to a particular leaf or a particular node. And if you actually consider data structures other than just binary search trees, you can actually differentiate between what the insert operation is going to do and what the query operation is going to do. And so really there might be a lot of extra optimization that's left on the table by only considering binary search trees, where if you actually generalize what data structure you're trying to make, it's possible we could have improved runtimes. So a primary idea along this line is to leverage the theory of efficient priority queues. So Fibonacci heaps and its derivative data structures offer improved runtimes if we restrict the operation set. So in particular, if our queries are only for the extrema, minimum and maximum, we don't require answering these operations that kind of have to do with the more middle element. Well, that means we can get insert in constant time. We can get a decreased key operation in constant time. We could even get this general merge function in constant time as well. So the kind of idea here is it possible to generalize efficient priority queues to support these other operations? And in particular, if we're able to do so, we might be able to get a sorted dictionary with better insertion times, better update times in general than a balanced binary search tree. So the intuition is balanced binary search trees require sorting elements on insert. That's clearly going to take logarithmic time, but we don't really need to sort on insert. So if we delay sorting until we actually have to answer queries, then we can just progressively sort our elements as queries are answered. Okay, and now there's been some work that has tried to do this already. In some models that we'll see are slightly limited, but the first category of work on this is deferred data structures, and this is publications in the 80s and 90s, so it's a little old, but so the first paper is by Karp and colleagues, Richard Karp and colleagues in SciComp of '88. And this shows that you can answer Q queries on a static set of n unsorted elements in O of n log Q plus Q log n time, and that this is optimal. And similarly, this was made into a somewhat, I kind of call this the semi-dynamic model, which is that we can also add insertions and deletions as in the category of queries. So we get these q prime queries, insertions, and deletions on a set of n unsorted elements, and then we can get time complexity n log q prime plus q prime log n. Okay, and the other kind of related work to lazy search trees and the problem we're considering is online dynamic multiple selection or multiple selection in general. And this is going to be pretty important for our work and the rest of the talk. So the multiple selection problem, if you are not familiar, it's pretty simple. You're given an unsorted array A, and you want to select the elements of a particular set of ranks R1 through RQ. So this means I just want to find the R1 smallest element, the R2 smallest element, and so on and so forth to rank RQ. So I have an example here. This is just an unsorted array A, and for example, I might have to select the element of rank 3, rank 7, and rank 13. And as you can see here, I've actually partially sorted this array A, which will be kind of the rough that we're going to try to bring into a dynamic model. And what I mean by this is I've taken the set of elements between any particular rank, and I've put them in their correct place without sorting the sets themselves. So we see you have 0 to 2 here, 5 through 2, or actually 2 through 6 here, then elements of value 6 through 11, so on and so forth. Okay, and similarly, I can actually get some bounds on what complexity is required of the multiple selection problem by considering these selected ranks directly. And this is going to be important for the rest of the talk as well. But I'll define this measure B here, and B is just the sum of the cardinalities of each of these individual delta i's. I'm going to call these gaps in the rest of the talk, and it's just the sum of the cardinalities of the delta I times the binary logarithm of n over the cardinality of delta I. And there are both lower bounds and upper bounds that say multiple selection is both required to take this omega b plus n time, and we can provide algorithms that match this in the upper bound. All right, so in multiple selection literature, this has been, this is also studied and generalized in various ways. The first paper here is by Barbet et al. And ESA 2013. And it says that multiple selection where the ranks R1 through RQ are given online and in any order can also be solved in optimal running time. And then finally, there has been some dynamic models studied in multiple selection. And this is another paper by Barbet et al. And this says that online dynamic multiple selection in optimal, OB plus n plus q prime log n is possible where it is assumed each insertion is preceded by a search for the inserted elements. And again, q prime is going to be the number of search, insert, and delete operations. Okay, so I've discussed the problem, discussed the motivation, and some of these related work that give partial solutions to the problem we're considering. However, they have some pretty big shortfalls that I'm going to highlight here and explain how our solution is different. So the first issue is that in the deferred data structuring literature, we don't consider the queried ranks. So we get these runtimes that are something like this n log q or n log q prime. And really, this is just leaving a lot of potential optimization on the table. We're trying to generalize efficient party queues, and say a Fibonacci heap is going to answer n insertions and q queries in O of n plus q log n time. So that's actually quite a bit better than this n log q. So we'd like to do a little bit better than these models. And then similarly, in these somewhat dynamic models, these so-called semi-dynamic models, we have this coupling of the insert and query operations. So they're all put in the same category, and we get these q prime log n terms. And this is a bit problematic because these two papers really only are interesting if you start with a large initial set of elements. Otherwise, if you're going to have a linear number of insertions, well, then this just ends up being, this q prime log n just ends up being n log n. And that's no different than a balanced binary search tree. And we're trying to do better than balanced binary search trees when possible. And so, yeah, you see the same thing down here. So there's some potential optimization that hasn't been explored yet. Okay, so what is the model that we propose? I'm actually going to delay the exact results of the talk until the very end. And this is because I need to describe the model in order for those results to make sense. Okay, so we're going to store the set of elements in our data structure in this partition into gaps based on rank key order. So I have this partition where this is similar to multiple selection, where all the elements in say delta 1 are less than or equal to all the elements in delta 2, so on and so forth. And we can consider how this partition will respond to dynamic operations as follows. So inserted elements, it's quite simple. We just place the inserted elements into the corresponding gap, one of these delta I, that respects the partition. So if I insert the key 8, well, then I'm just going to put this in our gap delta 3, and then we're back to the partition. Now, queries are going to be kind of interesting. It's actually going to be a generalization of the static multiple selection problem. And a query is going to fall into a particular gap and split the gap at a rank R associated with the query operation. All right, so let's say my query is a rank query for the key 5. So the query is how many elements in my data structure are less than or equal to 5? Well, then I'm going to end up associating rank R equals 9 to this query. And this is actually the answer to the query. And what I've now done here, this rank R equals 9 falls into the gap delta 2. And I have partitioned the gap delta 2 around this rank. So all the elements of rank less than or equal to 9 are to the left, and the elements of rank greater than 9 are to the right. This also coincides with the elements less than or equal to 5 and greater than equal to 5, or sorry, greater than 5. And so so, I then split the gap delta 2 into 2 new gaps based on this new partition. Okay, so how do I choose this rank R? Well, the intuition here is I want R to be exactly where I need to recurse in order to answer the query. So the rough idea is I really shouldn't need to sort the whole sequence when I'm answering a query, but there is going to be a particular part of the sequence that I do need to do some kind of ordering. It's actually going to be a linear scan at some level of the data structure in order to answer the query. And then kind of while I do this linear scan, I'll end up partitioning the data structure further so that it can answer future queries a little more efficiently. So what is the rank R? For rank and membership operations, R is just the rank of the queried element. And for select, predecessor, successor, minimum, and maximum, R is the rank of the element returned. And finally, for this split operation, which is kind of this query, sorry, it's an update that kind of has a query aspect to it initially as well, or is just the splitting rank in the argument. All right, so the intuition behind our framework, as I've kind of already mentioned a few times now, is that multiple selection now fits directly into the framework. If I were to have a multiple selection problem where I'm looking for the element of rank 3, the element of rank 9, well, then I have this partition into gaps as follows. But my algorithm will do this as a proof of the respective ranks of the returned elements. And similarly, binary search trees do fit directly in the framework. It's just as if I have queried for each of the elements that I inserted, and then all of the elements are in a gap of their own, and the whole set of elements are stored in sorted order. Now, priority queues are going to be kind of interesting. They'll actually correspond to a single gap delta 1. Okay, and now I can consider how the priority queue operations. I can now consider how the priority queue operations can be performed in the gap-based model. So extract minimum is straightforward. I perform a minimum query, and the rank R I've associated with minimum queries is just always going to be 1. And so I partitioned my gap delta 1. I find this minimum, and I split the gap into 2 new gaps. And then finally, I extract the minimum, and I am back to the case of a single gap. Okay, so let's talk about what the running time should be ideally in this gap-based model. So I'm going to use this measure B again, multiple selection literature, and we're going to generalize it to a dynamic model and try to match these multiple selection bounds. Okay, so the intuition behind B is that it actually characterizes the amount of information present in the current gap partition. Equivalently, it's the amount of work we have to do in order to get to the current gap partition. So we can see here if we do have the completely sorted order, well, then I have each of these gaps is of size 1, and it's just a log of n over 1, so it's just log n. So it's just n log n. Obviously, sorting takes n log n time, and so sorting is just a special case of multiple selection. So clearly, this should be n log n here. Now, the priority queue case, or really any case when I have just a single gap delta 1, well, I haven't actually ordered anything. B is going to be 0. Now, all the cases in between, we actually can show that B is actually going to be O of n log Q. So we see this n log Q term that was specified in related work popping up organically in our model. And the idea here is the most information is present when each of the gaps have about the same size. The number of gaps is bounded by Q, which is the number of queries. And so we plug this back into our B measure, and each of these gaps is going to be of size theta n over Q. And so we get this log term is going to be just log Q. And so that's how we get this n log Q. Okay, so we are going to try to achieve this optimal goal of B plus n time on an operation sequence that results in a particular set of gaps. However, we're going to have to go a little bit beyond this because we are considering dynamic operations where we can create gaps, we can delete elements, insert elements, so on and so forth. And then multiple selection will imply that this is optimal. Okay, so the first technical lemma we have here is that the change in B due to insertion into a gap delta I is going to be this omega log n over the cardinality of delta I. And I have a proof by example here. This is pretty straightforward, but I have the exact B calculated out for this particular gap partition. We see it's just 3 to n is going to be 16, so 3 log 16 over 3, 9 log 16 over 9, plus 3 log 16 over 3 again. And then this final individual single element gap is just log of 16. And when I insert my element 8 again, then I just go from 3 log 16 over 3 to 4 log 16 over 4. Rough idea, this is about the right amount that B is going to increase. And the proof is actually quite easy, but I won't go through the exact details here. And this is good because now we can leverage biased search trees to support our insert operations into gaps. So we're going to store the set of gaps in a biased search tree where gap delta I gets weight cardinality of delta I. So many of you are probably familiar with biased search trees, but I'm sure some of you are not as well. Rough idea is a biased search tree is just a balanced binary search tree where we have individual weights to nodes in the tree, and the idea is that we want to have the heavier weight nodes higher up in the tree, and that means that we have to spend less time to get to that node going from the root, so we can access it quicker. So if in my particular example here, I made sure that this delta 2 is the root, as there are 6 elements in gap delta 2, whereas in my other 3-element gaps, they can be a little further in the tree. This is obviously a little too small to see exactly the complexities, but what's going to end up happening with biased search trees is that you get access to gap delta I, or really to element I. It takes this log W over the individual weight of the element accessed. Well, W is the sum of all the weights. This is just going to be N. And so this is going to turn into this log N over the cardinality of delta I. This is exactly what our lower bounds said was necessary. And so, yeah, this is exactly what we want. Okay, now we can consider the query operations. And query operations are actually going to boil down to this kind of splitting operation where we split the gaps and we reorder the elements in the gap that we're splitting. And so we have this second lemma, which says that the change in B due to splitting delta I into gaps of size Cx and x with c greater than or equal to 1 is omega x log c. So I've kind of defined this in such a way as to try to make the complexity as clean as possible. But the idea here is I'm going to have this rank R that goes through the gap delta I, and then this is going to result in 2 gaps. One of them is going to be smaller. Let's make the smaller one of size x, the larger one of size cx. This ends up being the complexity required. And I can actually prove this fairly intuitively here. If we recall, B is the lower bound to multiple selection. And the way selection is proven, it's just this information theory bound where, okay, I have C plus 1x total elements here. And in order to find, I guess, the x, the smallest element, or really to partition the elements as such, well, there's C plus 1x choose x many ways that this can happen. I'm considering a comparison model, so each operation I do is going to give me a single bit of the final solution. And so the information theory lower bound says that I need to perform log base 2 of C plus 1x choose x many comparisons in order to differentiate which of the possible answers is the correct answer. That's in the worst case. And this is if you just do apply Stirling's approximation, this is going to end up being asymptotic to x log c. And here I'm using the fact that this log c, if c is 1, I still want this function to output 1, so it's going to be at least x time. Okay, now let's just take a brief pause here and see how this model corresponds to the priority queue case. So in the priority queue case, there's only one gap delta 1, so insertion is going to take log n over cardinality of delta 1. Well, cardinality of delta 1 is n. So this log 1 we've defined to be 1. It's just constant time. Similarly, remove the minimum element, we'll now have x equal 1, c equal to theta n, and so it should take O of x log c, which is O of log n time. So this is great because we're getting the granular complexities of priority queues back in our model. All these efficient priority queues, Fibonacci heaps, and so forth, they have this constant time insertion and logarithmic time extract minimum. And we see directly here why that this complexity is necessary. And yeah, we just have a little picture here. You see Cx is n minus 1, and so yeah, C is theta n. So yeah, you get this log n. Okay, so I'm actually not going to go into the technical details of how we support the splitting of gaps. This is the main technical challenge of our paper. And yeah, I wanted to keep this talk to be fairly high level. Unfortunately, the way we do it, we end up adding a log n additive term to insertion time. So I have this frowny face here because this is not optimal. But I can go ahead and now describe the results. Looks like I've given this talk a little faster than I expected, but there's a few slides left here still. But the first theorem, our main theorem, is that we can achieve a sequence. We can serve a sequence of n insertions and q unique queries in this O of B, and then I have to add these either a minimum of n log n or n log q terms. And so we're roughly a additive log n factor from optimal in this work. And yeah, because omega b plus n is a lower bound. And there are some interesting properties of the particular solution we developed. We actually only require a minimum of O of q or n pointers. Again, q is the number of queries. And this is interesting because, in general, these pointer-based data structures are a lot slower than the array-based versions. So a array is going to outperform a linked list when possible. Actually, in priority queues, you have binary heaps often end up being the most efficient priority queue in practice. And that's because the more complicated, theoretically efficient Fibonacci heap and its derivative data structures, well, they require something like 6 pointers per node, whereas the binary heap operates directly on an array. And so in order, and this is interesting because our comparison is binary search trees. Binary search trees have at least 2 pointers per node. So getting this q pointers in total really limits the number of pointers of the data structure if the number of queries is small. And so this is probably going to provide better constant factors, less memory usage, and then also better cache performance. Finally, I talked about dynamic optimality literature at the beginning of the talk, and it turns out that we can actually get the same benefits of this literature in tandem with the model we study. And although they are orthogonal, they do have some interesting properties when they work together. So yeah, in order to do this, I'll just use the splay tree. Splay trees can work as a biased search tree. And so the interesting thing here is that splay trees are efficient. I kind of showed the axis theorems. They're efficient when the queries are non-uniform. And this is actually also the case when lazy search trees are efficient. The difference is just that splay trees are trying to make the access efficient, which is generally going to be a query operation, whereas our data structure is trying to make the insertions efficient. And so splay trees are particularly efficient if you have a lot of queries, and lazy search trees are efficient if you have a small number of queries. But they still both operate over this non-uniform query sequence. That's the time when they shine. So I have the specific per operation results stated here in this slide. So I can do insert is going to end up being, instead of log n time, when I insert into a gap delta I get this log n over cardinally delta I. And then I have this additive log n term. But in general, unless this gap delta I is particularly large, the log n over delta I is going to dominate. So the fact we're not exactly optimal here is probably not particularly significant. Similarly, I can do a query that falls in a particular gap delta I and splits the gap into gaps of size x and cx. I can do this in x log c plus log n time. And the log n, although I mentioned in previous slides that x log c is what we were going for, the log n is actually required on average per query. So this does not actually come up in the theorem 1 that I stated on the previous slide. I can perform deletion, which take logarithmic time in the worst case. I can also perform some version of a change key operation, and I do have to have some restrictions here. And the rough idea is if I have this a pointer to a particular element, then I can change its key so that it goes closer to the boundary of delta I. And basically, the way this ends up working is that if I can do efficient splitting on a boundary, this x log c is, as I described, is just log n if I'm only taking off a single element. Well, then that means I can also change keys closer to that rank. This is just just the way that the gets generalized if I have a when you consider like decreased key of a priority queue that can be supported in constant time. When you consider it in this model where I have these multiple gaps and these splitting that can potentially happen on both sides of a gap efficiently, this is just the way that the mathematics comes out to support the operation efficiently. However, I can also just support it a change key operation in deletion and reinsertion, so I can always do it in log n time. Okay. I can perform construction on an initial set of elements S. I can do that in linear time. I don't have to pay the extra log n costs. And this is even true that I can, if I do insertions before I do any queries, then I don't have to pay the log n cost as well. Split is just going to be the same time complexity as query. And the actual splitting is just going to take place in the bias search tree in log n time, so that's absorbed in this log n term of the initial split of a particular gap. Merge can be done in log n time. Again, this is just a biased search tree merge function. Okay, I can do So we can do the insert, delete, change key, construction, merge operations in worst case time. However, we do require amortization in order to get the query and split operations. This is probably not that big of a deal, and that is because if you look at this term x log c, well, if I split the gap, if I have a particular gap delta I that has size theta n, and I split it into two gaps that are the same size, also of theta n, well, then my query actually can be linear time. So this is in contrast to a balanced binary search tree, gives you logarithmic time for every query. Our queries can be quite slow. However, we do less work over the entire operation sequence. And so this does mean that this data structure is not going to be something you want if you need to have fast query times in a per operation setting. It gives you fast insertion times, and then the work is put on the query. Also, if I do use a splay tree as a bias search tree, then merge and insert become amortized as well. Okay, so now I can talk about some of these applications, which I think are quite interesting when you start to beat the behavior of binary search trees in a tangible way. So balanced binary search trees, so what we can do is we can serve n insertions and q queries in O of n log q plus q log n time. Again, this is similar to the deferred data structuring literature, but the difference here is that I have completely decoupled the insertion and we have completely decoupled the insertion and query operations. And so I don't need to start on an initial set of elements. I can just serve any insertions, any Q queries in this same time complexity. I guess you'd say the other thing is that we also do, we support lots of different queries. They're not just membership queries. Now, the interesting thing is when you do have these non-uniform query sequences. And so I have just one example of a possible non-uniform query sequence where our data structure performs particularly well. And this is if you have n insertions and q over k queries for k consecutive keys. So the total number of keys requested is q, but I have them batched in this way where each of the batches is of k consecutive keys. Well, then my runtime goes to n log q over k plus q log n plus n log n. So the key point here is that this n log q term, which is likely to be dominating in the scenarios where we would want to use our data structure. As I described, if the queries, if you have a lot of queries, then it's no different than a balanced binary search tree. However, when I have a smaller number of queries, either a particularly small amount of queries or I have some structure in the queries, now I go from this n log q, I now have n log q over k. So essentially, I get the k consecutive keys likely for free because this n log q over k is probably going to be the dominating term. And I only have to pay log n per query. And in particular, the amount of work per insertion does not increase. And we can use this data structure directly as a priority queue or a double-ended priority queue. And we'll get log n time insert and also decrease key. And we can support a general operation set. However, there is a trade-off. If I do start querying for various ranks other than the minimum, I then introduce new gaps into the analysis. And this could slow future insertion or change key operations. We are trying to work to generalize the gap-based model even further. In theory, it is possible if you're looking at the minimum partial order to actually support the required, you can get rid of this trade-off, which would be nice. Couple last applications here. We can use our data structure for online dynamic multiple selection directly. Here, the interesting thing is that we don't have any restrictions. I don't know if you guys remember, but in the previous work on online dynamic multiple selection, they required that you consider a query to take place prior to every insertion at the particular rank that you're going to insert. And we don't have to make this assumption. And so we end up with something that's much more powerful, which is why we get all these different applications simultaneously. We can also use our data structure as a algorithm for incremental quicksort. So here, the interesting thing is that if you actually look at the internals of our data structure, which I have not described here, but we basically we store the elements of the data structure in this linear order of bags that are, the bags themselves are not sorted, but amongst the whole order, it's totally ordered. Similarly to how the gaps are done, we just take this one level further, and we can actually, as we answer queries, what we do is we just make the particular bags the elements are stored in smaller and smaller, and so we can actually do it such that we actually use a form of quicksort to refine the bag sizes. And this is interesting because quicksort is the most efficient sorting algorithm. It's quite practical, and so in order to, it's powerful to be able to leverage this existing theory into a data structure that has all these applications as well. And in particular, there's one thing we can do that's been studied in previous work, which is that we can return the q smallest elements of an initial set of n elements in sorted order. We can do this in optimal n plus q log n time. And we can also just sort any part of the array in optimal OOB plus n time, where I've defined this b as before. And here we really are doing our algorithm. What it ends up doing, our data structure, is pretty much the same as quicksort. There's a few minor differences, but it's really leveraging quicksort internally. So it should be interesting, both theoretically and practice. I will say briefly, we have implemented this data structure, and my implementation is not particularly well made, but it's a rudimentary implementation based on splay trees, and we have shown that it can outperform balanced binary search trees. It happens not until the number of inserted elements get to be about 1 million, so that's still fairly high, but it's still interesting nonetheless that this is an implementable data structure with potential practical applications. And that is going to be it here that I have. So I can take any questions if anyone has any.
I've been muted. Sorry. So first of all, let's thank the speaker. So I don't know. We'll try to clap. No, it doesn't work. Or
there we go. Yeah.
Perfect. Thanks very much for the great talk. I don't know what the rules are, but maybe it's a good moment to stop the recording so we sort of avoid situation in which we expose, other people than the speaker in this process. So, Othon, what is the usual way of doing it? Is it okay to stop it now, or?
Yes, I guess it is fine. We hadn't been recording previous seminars,
Right.
So I guess you can stop now.
Yeah, I think I attended a couple of meetings, and I think this was the moment of presentations where we're usually stopping recording.
Yes, let's stop it.
Yeah. Okay. So.